Hello, this is part 11 of Quick Precalculus Review for Calculus. In part 10, we fit an exponential function to two data points, neither of which represented the initial value of the function. And then at the end, we symbolically represented how exponential functions changed in that example. That's going to be our main mathematical focus in this video. We're also going to focus more on using Mathematica here, in particular using Manipulate to help us understand this symbolic change with exponential functions. But I want to start by starting in the same place I did in the last video. I want to go down to this Mathematica code here and enter it to help us analyze how families of exponential functions change as parameters change. In this case, the parameters are a and b in the function a times b to the x. First thing I want to do is just show you a cosmetic change. It's a little hard to see the axes there, so I can do axes, style, arrow, thick, type that in that way to show the axes in a thicker way that makes them easier to see. Let's make a few mathematical points here as well that I didn't really emphasize enough in the last video. First of all, if a is positive, which it usually is, then the graph is always above the x-axis, the y-coordinates are always positive, and in fact never zero. If b in addition is bigger than 1, that's exponential growth. The function is going up as x moves to the right, y increases as x increases. That's an increasing function. The slopes of this graph are always positive. Close to 0 over here and then get bigger and bigger as you move to the right. In fact, the fact that those slopes keep getting bigger and bigger also means this graph is what's called concave up. It looks like part of a smile when the slopes are increasing. What about when b is between 0 and 1? That's exponential decay. The function is decreasing. It's going down as x moves to the right. These slopes are negative. However, those negative slopes are getting closer and closer to 0 as you move to the right. So the slopes are negative but increasing in value, and therefore the graph is still concave up. It still looks like part of a smile. If a is negative and b is bigger than 1, that's a decreasing concave down graph. And if a is negative and b is between 0 and 1, that's an increasing concave down graph. In all cases except for when b is 1 and a is 0, the x-axis is what's called a horizontal asymptote. With exponential growth like this, the x-axis is a horizontal asymptote, you say, as x goes to minus infinity, which means that the y-coordinates of this graph approach 0 arbitrarily closely by making x sufficiently large in the negative direction. On the other hand, with exponential decay, the x-axis is still a horizontal asymptote, but now as x goes to plus infinity. You can make the outputs of this function as close as you like to 0 by making x sufficiently large. Alright, we'll talk more about asymptotes in later videos. Alright, on to the main content here. This was the example from the last video where we fit a unique exponential function through 2 points that are kind of weird looking points, but it came up with a pretty simple formula for those going through those points. Y equals f of x equals 3 times 1.2 to the x power. Alright, we want to understand this with Mathematica now, and in particular we want to understand this issue here. How is delta y related to delta x? It's kind of a complicated relationship. Delta y doesn't just depend on delta x, it also depends on x itself in this complicated way. You can make it a little simpler looking, I think, if you divide both sides by 3 times 1.2 to the x. In other words, if you divide both sides by f of x. You just get an expression that involves delta x, okay? In what I'm about to show you, it's very important that you use your imagination now, okay? So really stay with me here, get a piece of paper out, draw a number line on the paper, mark off a spot for x, and imagine x changing. If x moves to the right, delta x, the change in x is positive, and if x moves to the left, delta x, the change in x is negative. Here's what's going on with this particular situation. All right? I'm imagining x starting out at -2 and then increasing to 3 so that delta x is 5 in this picture. I've used show to plot the function itself like this with the plot command, to plot the points that I had, the data points, with list plot, and to also plot some lines that you see using the graphics command. I plotted 4 thick blue lines, one going from -2 comma f of -2 right there over to 3 comma f of -2 right there, so that delta x is increasing by 5. Then a second line going down to 3, 0. Then back over to -2, 0, which you can't see because I made the axis thick. Then back up to -2 comma f of -2, the original point. I continued the graphics line here with thick red line going from 3 f of -2 right here, 3 comma 25 twelfths, up to this point in the graph, 3 comma f of 3 is 3 comma 648 over 125 was this second y coordinate there. All right. How can we understand this equation in the context of this picture? Well, this picture is just static, so we're not going to fully appreciate the meaning of this equation based on just a static picture. We need an animation to fully appreciate it. But for the moment, let's just confirm that the equation works. What is delta y? Delta y is the length of the red line. It's the change in y. What is that length? 648 over 125 minus 25/12. The difference, the length as a fraction, is that. As an approximation, it's about 3.1. That's the length of this red line. What is y? Again, x is fixed at -2 here. Y is the length then of this vertical line there. It's 25/12. 25/12 is a little bit bigger than 2. So we need to divide 3.1 by a number a little bit bigger than 2. What do we get? We get about 1.48832. That is the ratio of the red line to the length of either of these vertical blue lines. About 1.5. This red line is about 50% longer than these vertical blue lines. What I want to show you to help you fully appreciate this equation, well, first of all, is we'll see that the quantity 1.2 to the delta x power minus 1 does equal the same thing. 1.2, what's delta x? It's 5 minus 1. This should equal the same thing. Yes, it does. 1.48832. Close to 1.5. So that's verifying this equation in the static situation. But to fully appreciate its meaning, we need to make an animation. I'm going to embed all this in a manipulate command. So all this stuff inside the show is going inside manipulate. Then I have a comma. You see the little red up arrow there? I need an animation parameter for manipulate. I'm going to call the animation parameter A. It's going to represent the first coordinate of the left endpoint. That's colored magenta here. I'll start it at -2 and go up to 5, say. All right, how do I want to make changes? I'm going to make my changes a little bit at a time and see that I'm doing the right thing as I go here. I'm going to change this -2 to an A, as well as this one. If I just make that change, enter it, I get an animation, and yes, that point is moving. Let me also make my label style large here, so you see the A better. So that point is moving. I also want to move the other point. Let's see. So I'll change this. What do I want to move it to? I want delta x to stay fixed, by the way. I want delta x to stay fixed at 5. So I'm going to make this an a plus 5 and this an a plus 5. That'll move the other point as well. All right, now I want to move the blue and red lines. Make this be an a comma f of a. Make this be an a plus 5 comma f of a. Make this be an a plus 5 comma 0, this an a comma 0, this an a comma f of a. I think that'll fix the blue lines. Yes, that rectangle keeps moving. All right, and it's getting bigger too. Now I want to change the location of the red line. I want to have an a plus 5 there and an, oops, 5, not b, and an a here. Then an a plus 5 here and an a plus 5 here. So effectively it looks like I'm changing all the -2's to a's and all the 3's to a plus 5's. All right, there we go. All right, what's the point? What's the punchline in all this? Okay, listen carefully. Think with me here. A is the starting value of x. Okay, if I don't animate it, then x is fixed. Delta x here, the change in x is still always 5. I'm imagining x itself changing, but delta x staying constant. I can pick any starting value of x that I want, like 2, for example. All right. The point of all this is if delta x is fixed, then this ratio is fixed. It's always equal to 1.2 to the 5th power minus 1. It's always equal to 1.48832. The ratio of the length of the red line to the length of either of these blue lines, these vertical blue lines, is always, in this case, about 1.48832, close to 1.5. So the red line, no matter what A is, the red line is close to 50% longer than the vertical blue lines. That's the point, okay? That might not seem like such a big deal, like such a important thing, but it is the essence of what makes an exponential function here. The relative rate of change of the function delta y over y, delta y over f of x, or this fraction, thought about in any one of those ways, is constant if delta x is constant. I'll say that again. This relative rate of change, delta y over f of x, the change in y over the original value of y, is constant when delta x is constant. It doesn't matter what x is. It doesn't matter what a is in this animation. All right? In this case, for this function, over a 5-year period, the overall growth in y is always about 48.8%. That's the point. Okay? And I'll let you think about that. I'll try to re-emphasize it in the next video.